Okay, this is the 5th seminar for the week. And, well, it's actually 2 of them. Mid-candidature reviews are a new invention out of the graduate research school. And part of that is to give a seminar and satisfy the paperwork that the GRS wants. And so we'll be having a few of these. The talks don't have to be all that long, and we've got 2 today, Tessa and CY. I'm sure this, CY's turned up. I was going to say it's been a big year for seminars, and it's particularly a big year at the present moment because we're having 4, 5, 6 a week at the present moment, and will be for the next couple of weeks as we go through the interview process. And Nick and Josh have been the organisers for seminars this year. But the real engine room behind this has been Cindy, because the seminar notices you see, they all come from Cindy. I'm not sure. Cindy, when I talked to her earlier today, said, I don't think Josh knows how to do this. As I said, there's another 4 seminars that I have to program between the 12th and the 15th of December. But she's done a fantastic job. I'm sorry she's not here just now, but well done, Cindy. Nick and Josh are doing them into 2014 for the first month, which is February, but I'm looking for volunteers for after that. I've already earmarked one person who's fighting back at the present moment, but I'll be seeing her in a week's time. And, beg your pardon?
Resistance is futile.
Yeah, but we need another person. So I'm looking for another person. So if anybody wants to put their hand up, please come and see me before the end of March. Okay, well, we're off today. And first up, Tessa.
Thank you. All right, let's see if I can work this thing. Cindy gave me strict instructions. So, afternoon everybody, and thank you very much for sticking around till this time on Friday to come and listen to us. Much appreciated, and thank you to the Centre for providing the beverage incentive. I'm sure it helped. So as David mentioned, this seminar is for the purposes of my mid-candidature review, which is a new process. So I'll start off by just reminding you about what my PhD is all about and the structure of my chapters. I'll then take you through some of the more interesting results from one of my chapters in particular, and then give you an overview of what stage my other chapters are at as well. So my work, as I'm sure most of your research is motivated by the fact that coral reefs globally are in a state of crisis. Drivers of change, such as these that you see behind me here, are causing widespread degradation on reefs around the world. And this is resulting in dramatic changes in the benthic composition of these reefs, but also in the structure of the fish communities associated with them. So a figure like this comes from a review by Wilson et al. In 2006. And what he's done is provided a summary of how fish communities are being affected by changes in coral habitat. And he's broken it down by functional group, and you can see he's got more sensitive groups like the corallivores, all the way along to algal feeders that are actually being slightly advantaged by this habitat degradation. But what really jumps out for me from a figure like this is the fact that there's no predatory group included. Where are the mesopredators that are resident on these reefs? And this tells us that there was just actually not the literature available to be included in a review such as this at the time. And I think this is a great omission and a large gap that needs to be addressed by our research. And this is what I'd like to begin doing with my thesis. So mesopredators are notoriously difficult to define. So for the purposes of this study, I'm defining them as medium to large bodied piscivorous fishes that are resident on the reef. So things such as members of the families Lichenidae or Serranidae. So I have 4 key research questions, and these pertain to each of my 4 chapters. The first is, what are the effects of prey availability on mesopredator condition, growth rate, and fecundity? Then, do mesopredators switch their diet in response to changing prey availability due to reef degradation? Thirdly, how does trophic structure change with reef condition, and what are the implications for the trophic role of the reef mesopredators? And then finally, I'm looking at whether predicted changes in coral assemblages moderate mesopredator prey dynamics. So for the purposes of this presentation, I'm going to focus on chapter 2, where we look at diet switching in mesopredators. So the work for this chapter was carried out in the Keppel Islands, and this group of islands are inshore on the southern Great Barrier Reef, and as I'm sure many of you know, these islands have been subjected to an increased frequency of flooding over the past years, and these floodplains carry a very high sediment load that, together with coral bleaching events, is causing dramatic decline in the health of the system. And this dramatic live coral loss has actually been incredibly well documented by a monitoring program that's been in action since 2004. So data like this shows us very clearly, and this comes from Williamson et al., 2014, that there is a serious decline in the condition of habitat in these islands. And my study period goes from 2009 to 2013. And you can see over this period, this decline was very consistent and quite steep as well. So reefs have gone from high coral cover to being algal rubble states. And associated with the shift in the benthic communities of these reefs is quite a key shift in the fish communities. And this is characterized by a shift from more planktivorous species, such as this Chromis natida, over there, towards more benthic species such as this territorial Pomocentris wardai, which feeds on algae. So you can see the planktivores are doing well at high coral cover, whereas these benthic territorial guys are actually being advantaged at low coral cover. So another thing that's associated with the shift in the fish community is that it's characterized by a shift in the dominant carbon pathways in the system. So we move from a system with pelagic carbon pathways towards more benthic carbon sources. And the question is, are the mesopredators in the system, such as coral trouts, able to adapt to this changing availability and change the carbon pathways that they're actually exploiting? So a neat way of getting at this is through the use of stable isotopes, a very elegant tool for this sort of trophic work. And for those of you that are not used to looking at things in isotopic space, on the x-axis here, we have delta 13 carbon, which tells us about where these predators are sourcing their carbon from. So on the more negative end, so on the left-hand side here, we have a more planktonic carbon source, and on this end, where it's a less negative signal, we have a more benthic carbon source. On the y-axis, we have delta 15 nitrogen, and this relates to the trophic level at which an organism is feeding. So something like a Pomocentris wardai, the territorial benthic algal feeding guy, he's going to have a carbon signal that's quite benthic, so it's sitting on this end of the spectrum, whereas something like Chromis natida is going to have a planktonic signal. And because in the plankton they're actually feeding on zooplankton as well as phytoplankton, they're going to have a higher trophic level. Then at a much higher trophic level than both of those are the mesopredators, like coral trout. And their carbon signal is very much going to reflect that of the food source that they're feeding on. So if they're feeding predominantly on planktivores, they'll have a planktonic signal. But if they are indeed switching their diets to take advantage of the changing prey availability, we might expect to see a slight shift in their carbon signature, such as that, which may also be associated with a change in their nitrogen signal as the systems degrade and the food chains actually become shorter. So the way I went about this is I collected muscle tissue from these study species. So first of all, the tissue for the Plectropomus came from archived muscle tissue samples, which was from a genetic study that Hugo actually did in the Keppel Islands a little while ago. And so those samples were stored in ethanol. Then I went out to the sites where these trout were biopsied and where he took these samples. And I collected these two prey species. So the Pomocentris wardai, which characterizes the benthic fish community, and then the Chromis natida, which characterizes the planktonic, or the planktivorous prey community. And then in order to just make sure that we're characterizing what constitutes a benthic or a planktonic signal in the system, I also collected these supporting samples. So turf algae would be the benthic carbon source in the system, whereas the planktonic source is obviously the phytoplankton. But by sampling oysters, we actually managed to concentrate that signal because these are filter feeders, so they're actually integrating the planktonic signal in the system over time. And then off to the lab, all of these tissues were extracted, cleaned, all calcareous matter taken out so we don't confound the carbon results, and then freeze-dried and sent to Canada for analysis at the GLIA lab, where they analyzed stable isotopes. And these are the results. So again, we have carbon source on the x-axis and nitrogen or trophic level on the y-axis. And at the bottom here, these are the results of the algal samples. And just to help you read the figure a little bit better, the colors here are associated with species, and the shapes of the symbols tell you which site that they were sampled at. So on the bottom here, as we would expect, the algae are sitting on the bottom of the nitrogen axis, they're the producers in the system, but that widespread variation in their signal tells us that there's something else going on there, and it's likely due to the fact that there's detritus contaminating these samples, both from the coral reefs themselves and from land-based sediment. But nonetheless, the signal is reflected in the fish that are feeding on this turf algae. So the Pomocentris water have got a similar carbon signal, but then feeding at a higher trophic level, being consumers. This group over here are the oysters. So you can see they're clustering towards the planktonic end of the carbon spectrum. So they're really characterizing the planktonic signal really nicely for us. They're consumers higher on the nitrogen scale. And then above them, Chromatoptida, also planktivorous, but just sitting higher up the food chain. And then this group up here are the trout. And as you would expect, they have the highest nitrogen value in the system, being the top consumers. But there's quite a lot of variation in their carbon signal. And what's interesting to me is that a lot of this seems to be structured around site, if you look at how the shapes are grouping. So there's something about the place or the environment where these fish are being sampled that is actually having an effect on their carbon signal. There also seems to be an interesting pattern here where these symbols here that are at the highest trophic level are also on the more planktonic end of the carbon axis. So on reefs with on the reefs where they're feeding on a planktonic source, they're at a higher food level, so the food chain is longer. On this end where they're feeding on benthic prey, the food chain is actually shorter, they're sitting at a lower trophic level. So the way I investigated what's actually structuring this Delta 13 signal is I looked at a number of drivers, including live coral cover, which is a proxy for habitat condition or habitat degradation, distance from mainland, and we would assume that trout that are sampled further offshore will have a more planktonic carbon signal. Total length was also included because we know that trout switch their diets. As juveniles, they feed largely on inverts, whereas as adults, they actually switch their largely piscivorous diet, and that's at about 21 centimeters total length. And then, as a random factor, I also included year or site, so the place and timing of sampling, just in case there's an effect hidden in there. So the two models were either a linear fixed model, including those factors, or the other candidate was to use the random effect in the model. And based on a model selection process using AIC values, it actually turned out that this random effect really didn't improve the score of the model at all. And what was also interesting, that from these two models, the total length of the fish came out as a non-significant factor, which means that we've actually sampled substantially large fish, or so that we're not having any confounding effects from ontogenetic diet shifts in the signal. So that's the model we ended up with, and it becomes a bit of a brain twister now, because the Delta 13 carbon over here is now on the y-axis. It's no longer on the x-axis. So we have a benthic signal here, a planktonic signal at the bottom, and on the x-axis we have live coral cover. So let's bring back these guys to make it a little bit easier to visualize. And you can see that where we have high coral cover at this end, we're finding a more planktonic signal in the trout's carbon value in their tissues, and at lower coral cover, they're actually showing a more benthic signal. Then in terms of distance from mainland, as we would expect, a similar pattern. So fish that are sampled closer inshore have a more benthic signal, those sampled further offshore, a more pelagic signal. And then in terms of what's happening with the trout populations with this coral decline, we actually see that their populations are remaining relatively stable. There is indeed a decline as coral cover declines, but if you look at the slope of this line, it's very, very, very small. So it actually indicates that they are somehow managing to maintain their populations at a relatively stable level, which seems to be a good news story, right? But there's a little twist in the story, right? So this is the carbon to nitrogen ratio. And this carbon to nitrogen ratio tells us about the ratio of lipids to protein in the tissues of the fish. So on this spectrum, if we have a high ratio, so high lipid to protein ratio, that means we have high fat stores in the fish, and the fish are likely to be in better condition. On the other end of the spectrum, we have lower fat stores, and the fish are in worse condition. So if we look at this in relation to live coral cover on the x-axis, we see that on the more degraded reefs, trouts actually have a lower carbon to nitrogen ratio. But up at the other end of the spectrum, at high coral cover, the fish are doing much better and they're in a better condition with higher fat stores. So in summary, we found that there's clear trophic structuring within these communities, despite the fact that there's been obviously very severe habitat degradation taking place. There's been a dramatic loss of live coral cover that's associated with a shift in the fish community, and this is characterized by a shift from planktivorous species to more benthic-feeding species. And associated with this shift is a change in the dominant carbon sources and carbon pathways in the system, from more planktonic carbon sources towards more benthic carbon sources. And the stable isotope results certainly suggest that trout are able to adapt their diets to take advantage of this changing prey availability in the system. But there also seems to be an associated cost that we see through this carbon to nitrogen ratio, where trout are actually showing a decline in their condition. So if we think about this a bit, it's fantastic. We've actually confirmed a lot of the results from previous findings that have found trouts to be highly adaptable species, great generalists, which is good news. But there's this caveat where we should take heed that there are these sublethal effects that in the long term may actually show negative effects in the population. Fish are likely to potentially have declining growth rates, reduced fecundity, and less lipid stores to be able to withstand periods of disturbance. And I think it's also very important to consider the specific context of the study, so where it took place. And there's been a lot of work in the centre on the MPA system surrounding the Keppel Islands, and they've been shown to be highly effective at maintaining high recruitment rates for coral trout in the system. And as we all know, in most parts of the world where we find coral reefs, that is very much not the case. So they're very unlikely to have that kind of effective management on their reefs. The other final consideration is the role of structural complexity in the system. So the disturbance that's happened here is very recent. So there might, despite the loss of live coral cover, there might actually still be a substantial amount of structure in the system. And as this begins to decline with time, we may actually see more impacts on both the predators and the prey on which they're feeding. Right, then I'll take you on to just the last bits and show you what's left for me to do in this thesis. So don't worry about the text for the moment, I'll take you through that in a minute. But just have a look at the colours. So this sort of greeny teal colour over here, that's the bits that have been done. Those are all complete. The orange bits over here, that's what I'm currently busy with at the moment. And then the grey bits are what still needs to be done. So the first chapter, my fieldwork for this was based in the Seychelles. So we had a month-long trip there in April this year. Spent lots of long, happy hours on the water, spearing Stylophora with these little rafts. And all the fish were processed. I took all the morphometric measurements. The oatlets have been read, histology sections have been read, and a lipid analysis is underway in France with that data due at the end of January next year. And then it's all ready to go for analysis and write-up. The second chapter was the chapter in the Keppel Islands, which I've just taken you through, and that's hopefully nearing submission in about the next month or so, a month to 2 months. The third chapter was also the fieldwork for this happened in the Seychelles. So we're aboard this vessel Lemaitre from the Seychelles Fisheries Association with this bunch of dubious-looking characters. And then, so that data is all ready for analysis and to be written up. And then my final chapter is based on Lizard Island. So we set up a patch reef array there in October last year. We have 24 patch reefs. And since then I've had 7 trips to the island to monitor the recruitment onto these reefs. And then at the moment I'm busy trialling experiments for a caging experiment with predators, which will take place after this current recruitment season, so March, April next year. And then that needs to be analysed and written up. And then just finally to remind you of the publications that I plan to see come out of this PhD and the sorts of places that I'd like to be publishing them as well. And with that, I'd like to thank my exceptional team of supervisors. They really are an amazing crew to have behind me. And to all the people that have helped me in the field, in the lab, and just with general advice and guidance and support. It's really been an amazing ride so far, and I'm very glad it's not over yet. So thank you.
Questions?
Is there any reason you use distance from the mainland rather than distance from the Fitzroy River? It's a very different metric.
Yes, I agree.
On the victory.
I agree, and I would actually like to have a look at the latter.
Yeah, you should do that because they're totally different.
Completely.
The capitals are all about the same distance from the mainland, roughly, but in terms of distance from the Fitzroy River mouth, they're structured out in space.
Agreed. I think that's definitely something to consider. Those particular sites are all sort of in a fairly narrow band in terms of longitude within the capitals. So it's not too big a difference, but definitely I agree with you that that's potentially something to look at for sure.
Can I ask about the C2N ratio? Why did you take the samples for to measure the C2N ratio?
So that was part of the stable isotope analysis. So all those white muscle tissue samples that we took, it's just the percentage of carbon to nitrogen in actual muscle tissue. So it's part of that process.
That's really beautiful. These are my returns. I was just wondering, because you said you took archived tissue.
Yeah.
Did you have tissue sort of pre-flood and post-flood? Like, have you been able to?
Yeah, there is, but unfortunately it's not as clear cut as that. So the samples unfortunately don't cover enough of a geographic range pre and post flood to be able to see that effect. So a lot of the samples, say from a site like Egg Rock, are post flood. So it's a bit lumpy in that way. So it's a little bit difficult to tease that out. The other thing with that as well is that because it takes a while for those signals to become integrated into the tissue in the fish, it's not as immediate an effect as you would like it to be, I guess.
You go.
Is there variation in that for that carbon to nitrogen ratio? Is there variation in that ratio throughout the year, in various periods of the year, where they're feeding more or feeding on different species?
There would be. In this data, again, there won't be that just because, I mean, you know, from those samples, they're very much at certain, they when the field trips took place. But so the reference that was on that slide from Estrada, she did a whole bunch of work on looking at that in tuna. And she's one of the few people that have actually looked at the carbon to nitrogen ratio in consumers rather than using it for nutritional quality of food sources and things like that. And she actually had this temporal monitoring. It was really amazing. So looking at their breeding cycles and seeing how their fat store changes depending on whether they're producing eggs or building up to it and that sort of thing. So yeah, that definitely comes through.
One more. You've used coral cover.
Yes.
One of the main things that happens with flood plumes from the Fitzroy is that it affects different depths of different coral because of freshwater layers and things going on. Do you think your coral cover metric is a good at all depths? Is an accurate representation of the actual coral present at 10 metres as well as 1 metre?
Yeah, so this is all, that data is from Dave Williamson's, and I mean the rest of it. So actually definitely a better person to answer this because he spent more time collecting that data. But so the data that I used for that was at a consistent depth across their table. So it was all comparative, at least within this data set. But I don't know, Jeff, do you have anything to add?
I'm not sure what depth that is. That's just up the slope, I think.
Last question, Morgan.
Yeah, did you end up filtering it for species? Because obviously Ashley showed there's different ratios for maculatus and leopardus.
Right, yeah. So all of these samples are actually, they're maculatus, right?
Yes, maculatus.
They are. So yeah, it is consistent within that.
Good. Thanks very much indeed, Tessa. The second presentation is CY.
Keep going. Jump. Like a school presentation.
Thanks for coming. and since this is the first time of the mid-candidate review, so I'll present this review seminar as a talk talking about story happened just next to our door, which means the GBR, in particular the central GBR Townsville region. So it's a long-term change in the structure, the inshore reefs in the central GBR. Okay. So the AIMS long-term monitoring team has put a lot of efforts checking the coral cover in the GBR for the last decades. However, even using the same data set, they come out with a contrast result. For instance, Hughes Sweetman 2012 suggests that there was no regional changing of the coral cover in the GBR, but the Diaz 2012 saying that the latest data saying there was a 50% of the loss of the initial coral cover in the past 27 years. If we accept Sweetman's data, which means there was no regional decline, which is we are happy to accept. But it's a regional scale result. So there might be some information hiding behind the big scales data. So let's have a closer look of the 2012 result. So if we divide the GBR into different sections, which means the north, south, and north, central, and south GBR, then all regions have not been affected equally. For instance, the northern GBR was fairly constant in terms of coral cover, but the central and south GBR was declined dramatically. So that's but those results are using the coral cover as an index. So it might hiding some important information, such as the change of assemblage structure. So if we get back to the Sweetman's result, there was no changing of regional scales. But the recovery in terms of color can hide major changes in assemblage structure. For instance, in the Moria, the coral cover can return to pre-disturbance level in 24 years, but the assemblage structure shifted from dominant by Acropora in 1979, shift to dominant by Pocillopora in 2007. So this highlights another question: is coral cover is a good enough indicates to detect the change of the coral reef changes? Because there are also other issues cannot be answered if only using coral cover. For instance, coral cover cannot pick up potential important changes in assemblage structure. For example, have we lost any taxa, and have any taxa benefit from those repeated disturbances? And this one relevant to the hypothesis of winners and losers. So the winner and losers means that the life history theory suggests that a group of corals or species share the similar traits, have a similar condition in response to disturbances, and they got some in response to environmental conditions, and then there are some predictions of different life strategies. For example, weedy species such as brooders like Stylophora, Seriatopora, and Pocillopora, because they produce in early life, so they can get benefit in environment which is more frequent disturbances. But in stress-tolerant species such as Montipora and Porites, they put more effort to resist to disturbances. And the last one is the competitive strategies such as Montipora and Turbinaria. They can get benefit if during a period without major disturbances. So in this talk, I'm going to describe the 15 years of the change in assemblage structures in the inshore reef of the central GBR, which means the Townsville and the obvious island. And in particular, I'm looking at abundance, which means colony number. Unlike other studies using coral cover as an index, the reason using abundance because the abundance, which means the increase in degrees of colony numbers, can indicate the event of recoupment. And if we just using coral cover, we can't integrate the data in this way. Then also, I'm also looking into the genetic richness and assemblage structure. So let's have a look at the study. The 6 spell chances was laid out at 2 different depths, 2 meters, 2 meter and 5 meter and 4 sites, including Little Pioneer Bay and Southeast Purus in Obvious Island, and make a Nelly Bay, Jeffrey Bay, and Maggie Island. And all the colonies larger than 5 centimeters in diameter will be recorded and identified to genus level. And between 1999 until 2013, 10 times of survey has been conducted. And I will start the result by putting all the data together as a regional result of this area. So the data shows the average colony abundance through time. And only pick up 5 time points before 1998 breaching event, after 1998 breaching event, 2004, 2005, and 2013. Those 5 points, we survey all the A sites in those 5 time points. So I pick out those 5 times to check the change of coral abundance through time. So there are a few points can be highlighted. The first, the abundance in 2013 was 50% of as the level before 1998 breaching event. And there was an initial decreasing due to the 1998 breaching event, but the average colony abundance has never been recovered. And the third one, the low abundance in the 2013 was due to the recent major disturbance such as cyclone Yasi in 2011. So since 50% of the initial colony has been lost in the past 16 years, have we lost any taxa? So the data shows the generic richness in the regional scale through time. Then it shows the generic richness was fairly constantly at around 45 genera through time until 2013. Between 2005 and 2013, we gained 3 genera but also lost 2 genera. So the result tells us, so there was a very little change in the genetic richness. And since there was very little change in the genetic richness, how about the relative abundance of each genus change through time? So the data shows the relative abundance of the top 10 abundance genera before 1998 breaching event. And so just have a very glance look of these figures. So the first one shows it's very little change of the assemblage structure through time, even though there was a mass disturbance like the 1998 breaching event and the cyclone Yasi. But recently, just after the cyclone Yasi, a few genera got benefit from the disturbances, such as the Montipora. Montipora got the relative abundance of Montipora increased, but in the meantime, the relative abundance of Acropora decreased. So, which is a very interesting result because the Montipora belong to the stress tolerant species, and based on the life history strategies, the weedy species should be the one got benefit rather than the stress tolerant species. So how those weedy species behave? So this figure shows the relative abundance of the 4 weedy species, including Pocillopora, Stylophora, Mesopredators, and Seriatopora through time.
That's okay. Yeah.
So just another glance look. So actually most of 3 out of the 4 genera were decreased in terms of relative abundance, the only Pocillopora. However, the relative abundance still very low, it's around 1%. So this means the brooding genera, weedy species, didn't get benefit from the repeated disturbance, which reject the prediction of the life history strategy. And then we get a more closer look into the how everything changed at each site. So this figure shows the average colony abundance through time at 8 different sites. From the top to the bottom is Nelly Bay and Jeffrey Bay Maggie Island and Little Pioneer Bay and Southeast Cruise in Obvious Island. And on the left-hand side is the shallow reef, and the right-hand side is the deep reef. So the letters above shows there was no major the same letters above shows there was no major difference between the time point. And the first thing I like to highlight here is at each side this shows a number of cycles of disturbance and recovery through time. And the second one is only 5 out of 8 sites were affected by the 1998 bleaching event in terms of the average colony abundance. And 3 out of 8 sites wasn't affected by the bleaching event, but they might affect by the following disturbances. And among the 5 sites, only 2 sites out of the 5 sites affected by the bleaching event recover in terms of the average colony abundance, and with different time frame. At the deep water of the Jeffrey Bay, the average colony abundance returned to similar level in 2 years, but in the shallow water of the Little Pioneer Bay, the recovery took 6 years to return to pre-disturbance level. So have we lost, since all the sites showing the fluctuation of average colony abundance, have we lost any taxa at each site? So the figure shows the average genetic richness at each site through time. So actually, the genetic richness was following the change of the colony abundance, which means low colony abundance, low genera can be found. But in the regional scale, we didn't lose a lot of the genera, even though there are some loss in each site in the site scale. So how is the assembly structure changed through time? So if we combine the two different changing patterns, including the colony abundance and also the assembly structures, there are 5 patterns can be detected, like the recovery or reassembly. Recovery but no reassembly. And I will go through each of the patterns in the following slides. The first one is in the deep water of the Jeffrey Bay. So there are 4 time points you can pick up. The first one is the assembly structure before 1998 bleaching event, showing the green color, and the red color showing the assembly structure after the 1999 bleaching event. And the yellow color shows the highest colony abundance we call after 1999 bleaching event. But that doesn't mean the colony abundance return to fully recover already. It just shows the highest we call. And next one is the last survey, the orange color. So in the deep water of the Jeffrey Bay, the colony assembly returned. The average colony abundance returned in 2 years, which means we returned at 2000. But the reassemblage took 14 years to return to pre-disturbance status. And the second one is in the Little Pioneer Bay. The assemblages, at Little Pioneer Bay, the colony abundance recovered, but no assemblage. There's no assemblage happen. And the third one is the 2 sites at Nelly Bay. No recovery, but reassemblage in 2 years. And the fourth one is no recovery and no reassemblage. It happened in the shallow water of the Jeffrey Bay. And that's why those 3 sites wasn't affected by the bleaching event. However, just using the shallow water in Southeast Cruise, even though the assembly structure wasn't affected by the 1999 bleaching event, but following changing of assembly structure shift to another different status, and also then affected by the 2011 cyclone Yasi. So that's a summary. So at the regional scale, the colony abundance dropped initially after the bleaching event, but also recovered. But also increased after the bleaching event, but it never recovered to pre-1998 bleaching event. And second one, between the 1990 and 2012, there was a 50% of loss of the initial colony. But this 50% loss was mainly due to the recent disturbances like the cyclone Yasi. And even though a lot of coral numbers lost, but we didn't lose any major taxas, and even though some only lost a few rare taxas, and also gained other few taxas. And among those, even though the genetic richness was fairly stable, only a few changed in the relative abundance. And the winners can be counted as the increase of relative abundance, like Montipora and Porites, those stress coral species. And the losers are weedy species, Pocillopora and Stylophora, which is the consistent result as with the prediction from life history strategy. At the size scale, all the size shows the number of cycles of recovery driven by the recruitment. And the genetic richness at each site was following the change of colony abundance. And the several patterns can be identified at the AO site. So the conclusion, there are repeated cycles of increase in terms of colony abundance driven by the recruitment. However, there is no major change in the assemblage structures, particularly at the regional scale. And there we just lose a few taxas, but also we get another taxas. So if we combine all the data together, there's a good news that even though the colony abundance is in low in 2013, however, the coral assemblages in the Inshore Reef or the central GBR still maintain their resilience ability and has the potential to recover to pre-disturbance level if given the period of time lag of major disturbances. Thank you so much.
Questions?
I was wondering, do you also look at the size structure of your colonies? Or
No, just colony number.
So number. Do you have any sort of, since you didn't look at it directly, any idea of whether the sites that didn't appear to be affected by, for example, bleaching events, whether that, if you had looked at size structure, whether that might be important, or?
Could you please repeat your question?
So, although you didn't actually look at it directly, when you were doing the surveys, for example,
yeah.
I don't know how many of these you've had a chance to do, whether the sites that didn't recover, or the sites that didn't get impacted by the bleaching event in 1998, according to the metrics you looked at, whether the size structure of the colonies might have changed? You're not sure.
I'm not sure, but I think
like we're bigger colonies.
the bigger colonies may get some partial mortalities, but the small one may just got wiped out.
Sites that were dominated by large aquaphora colonies, abundance is not a good measure of effect. So at one of those sites where we didn't find an effect, we also recorded 90% mortality of aquaphora licenses. So abundance is not necessarily a good estimate of the effect of bleaching.
In your introduction, you showed those two data sets, which are part of the same data set, of course, from Sweetman and Diarth, just extended a bit, and a somewhat different interpretation, as you know, even though Sweetman was an author on the second one too, but anyway, let's not go there. And remember, they're all mostly mid-shelf reefs, and a few out-shelf reefs, not many inshore reefs. There is the other data set I assume you're looking at from AIM's Marine Monitoring Program, called the Marine Monitoring Program, which looks at inshore reefs that Angus Thompson runs, and we've got we've got 7 years of records of that now, and now I'm aware they're not published in papers, but they're in peer-reviewed reports that have numerous more sites on the inshore GBR that are comparable to the sites you're looking at. And they show, in general, the same sort of decline in overall coral cover as the LTMP does on the inshore reefs in general. That's a very broad statement, but in a general sort of way, they're really worth looking at.
And also their data didn't put the result here, but the AIMS long-term monitoring team, they also divide their result to different subregions like inshore, outer reef, and they also come out another conclusions. Those inshore reefs were more affected by the disturbance in the past.
Really, you could just reflect a little bit on looking at abundance as opposed to cover. So, and it gets at the colony size issue a bit. You know, when you're looking at the reorganisation of the reefs, if you'd looked at cover instead of abundance, do you think you would get a different pattern? For example, if you've gone from a lot of large acroporas to the same number of small acroporas because you're in a recovery phase, do you think you'd see bigger shifts in that multivariate space, or can you just reflect on your expectations or how you think those two different ways of looking at the benefit assemblage may influence your interpretation of results, I guess?
I think the coral cover and abundance are two different aspects to look at the change. So yeah, I agree if I use the coral cover, use the actual abundance of all the coral of each channel, yeah, the result might be different. But the result here is we try to look we try to focus on the recoupment, which means the potential, showing the potential of the reef can be returned or not.
So making the assumption that if there's the same number of colonies, then you're going to end up with the same structure, ultimately. Okay.
Only about a week ago, we had a seminar in this room from John Pandolfi, where he talked about those reefs of Polaris. Maybe not the same one you looked at, but his story is that, and there's more data from Tara Clark's work in the same area, not fully written up yet, that the change in genera, in a sense, through time has been driven through by a combination of acute events, bleaching in recent times, maybe cyclones in the past and so on, and chronic water quality stresses. Are you trying to take that into account as well with what you perhaps have there at both Magnetic Island and in the Palms are extreme events, whether they're bleaching or cyclones or cyclones for that matter, combined with a chronic poor water quality that impedes recovery of some species? Remember, that's what John Pandolfi is saying. Now, of course, whether you believe all that's another matter. John obviously does, and I think I do sometimes. Yeah. But that's the theory that's going around, is that we've changed at Polaris from a cropper to loosely massives, I guess you'd call it, about in the 1930s. The reason given is some sort of chronic water quality problem that's unspecified at the moment, which is a problem, but anyway, and that you've got that chronic water quality problem in the Palms all the time now. So I think you've really got to look at that. Are your results explainable in terms of the recovery of both species composition and cover, in terms of both acute disturbance plus long-term chronic stress as well?
I think because there's another issue about the shipping baseline. So because our data only start from the 1998, and yet for sure there might be some changes before that, but at least this is what we got from our data. And our survey was quite constantly in the same kind of permanent change set. So I think that's quite good confidence to how data flow. Because I'm sure the water quality or some the stress like water quality might affect the result, might affect the coral colonies, but they might be under stress, but they still can survive.
And if you go into what John's talking about, the only chronic water quality stresses I can think of there are maybe increased turbidity because of increased sediment delivery and resuspension. It's happening there all the time now, chronically. And that will change the light climate at different depths and different ways, and there'll be subtle changes in, I would have thought, speciation of coral, depending on their light gathering ability, I'll say loosely, for lack of a better term. And perhaps shift between autotrophic and heterotrophic feeding corals as well.
Last question.
Thanks, everyone. I think the thing you're saying, like the weedy species and your stress tolerant species came out different to what you'd expect to see in sort of a stressed environment. Your tolerant species hung on your weedy species buggered up, which seems kind of interesting. Yeah. But do you think that sort of means maybe we need to relook at this kind of life history traits and what we're actually talking about, or do you think it's just a different or a smaller section of a bigger trend, and maybe the weedies will take over after that, or I don't know. What do you think?
I think that we might want going to work in the next year to try to look at the life strategy again. We can come out different stress groups.
Thanks very much, Steve.